Okay. Hi, everybody. My name is Sasha, and today I'm going to be delivering a lecture called An Overview of Medical Survival Prediction as part of the AIMS 2022 AI in Healthcare curriculum on the side of applications of AI in medicine. Now, this was supposed to be delivered live on March 19th. That did not end up happening. I was unavailable at that time, and I have been a little bit sick for the last few days. So hopefully my sniffling is not going to bug anybody too much. But without further ado, let's get started with today's presentation. Just a few things that I'm going to be talking about today. First, I would like to motivate the problem of survival prediction in a medical context. I'll go through a summary of the approaches that are often used in this domain. I'll talk about how we like to measure model effectiveness, how we can figure out which model to use, what is applicable in what context, etc. I have a section that goes into some examples of the different model classes that I'll be talking about and showing some of the medical applications of those models. And at the end, I have a demonstration of one of the University of Alberta born survival prediction tools. A lot of what I'll be talking about in this lecture is taken from this kind of half review paper, half novel introduction of an evaluation metric paper. This is something that I worked on with my colleagues Hamza, Brett, and of course, Dr. Greiner as well a couple of years back. So this is a field that I am decently familiar with. If you're interested in more information about this, I would say definitely begin looking over this paper. Although I think including the appendix and the references, it ends up being about 60 pages of text. So I'm going to try to basically today distill all of the best information out of this paper for you guys, and you won't have to slog through too many of the details here. Okay, so let's try to motivate this problem here. I first want to talk about what survival prediction is. Generally, this is agreed to be the study of time of the time period that it takes for some event to occur. And this encompasses many statistical techniques, and now more recently, many kind of more machine learning or artificial intelligence techniques. This is closely related to the field of survival analysis, although survival analysis, as defined by Dr. Greiner in the previous paper, tends to focus a little bit more on the features that are maybe important to predict survival, trying to dig into why the models make the decisions that they make, whereas survival prediction as a task is very concerned with the actual outcome, the actual prediction of either the time until an event happens or whether an event will happen in a specific time period, etc. One may ask, why is this its own field? Wouldn't just a simple regression task work if you're predicting a real value? If you just trained a regular linear regression model, wouldn't that just suffice? And the answer, of course, is yes and no. I'll get into this in just a few slides from now, but there are some particularities about the survival data that is available to scientists to try to solve these problems that make it just a little bit more difficult than it would have otherwise been. I first want to talk about what is survival analysis or survival prediction within medicine. A literal interpretation of this would be to predict, say, something like the time until death. So hence the word survival. If a patient is surviving until a certain point, then you would use survival prediction to try to predict at what point the patient would survive up until. I have a picture up here of a concept art of a watch that a Kickstarter campaign was built around. Basically, you would answer a number of medical questions and you would have this watch that basically count down the days until it predicts that you die, which I don't think it got fully funded. I'm not sure why many people would want something like that, but that would be an application here of literal survival prediction. But beyond this, survival really can just mean survival of a system. And a system can be, for example, an individual that is struggling with addiction that has not experienced some kind of relapse event. So the survival of a system would be to continue without a relapse event. And if a relapse event did happen, that would be the death of the system, right? It could be a sick individual that has gone on without urgent unplanned hospital readmission. It could be a cancer patient without metastasis. And if those systems are surviving, that's great, but you may want to be predicting time until there is some kind of an event that happens. Survival analysis or survival prediction doesn't always have to be applied to the medical domain. There are many other applications, often in, say, like a warehouse scenario. You might want to predict, say, how long is it going to be until one of my machines fail? And so that would be like a failure of some kind of system. You would want to predict the time until that. Oh, my slide is stuck. There it is. Okay. So let's try to set this problem up, and I'll continue using this example for the next little while, hopefully to give people a good intuitive understanding of how this is going to work. So imagine you have a data set with what you believe to be survival time as the target. You can see it here. Hopefully my mouse is captured in the screen share, but I'm not sure if it will be. Each row in this data set is a particular patient with a number of features. So if you are at all familiar with machine learning, this seems like it would be probably a pretty easy problem. Like I said, you could probably just lean on a very common technique such as linear regression, right? So let's say you do that, right? You have this variable time and you want to use a number of features to predict time. You could fit a simple linear regression model to try to predict this value. So here I have a very simplified version of what that might look like. Say we're only using one variable to try to predict the time here, and you can just fit a very simple line. But the time variable, because of a number of medical constraints and clinical and kind of just general constraints, is not really actually what it seems to be. This time is actually not generally time until event or time of survival. It actually is more aptly called time until event, because the way that medical trials work, the way that studies are defined, there are going to be a number of data points, a number of patients within this data set where their survival time is actually not well known at all. So at this point, we need to introduce another, I guess, kind of target feature, another feature for each patient called the censoring bit. And I'll explain in just a second what censoring means. I think I have a graphic coming up. Wow, my slides really don't want to flip right now. It's flipped on this screen, but not the one I'm presenting, which is great. There we go. Okay. So imagine you have 5 patients here, and you begin a study tracking these patients in the year 1990. Up until the point where the study ends in 1995, you have patient 1 and 2 who pass away. Right? So, patient 1 maybe survives about 4 years, patient 2 survives 3. For those patients, we actually know their survival time. Unfortunately, though, patients 3, 4, and 5, they are what we call censored patients at this point, because either they dropped out of the study entirely, as is the case with patient 4 and 5, or the study ended before we could even figure out what their survival time was. So at this point, the last we saw from them, the last we heard from them, they are still alive. And so it's difficult to try to infer what their actual survival time is, because clearly, their survival time is going to be somewhere in the future that we don't have access to in the data set. This can cause pretty significant problems. One might say like, oh, like just get rid of the censored patients, right? Like you don't even like need to know. not only would that skew the data set, but also in most of these data sets, they are like at least 70% censored. So you would be giving up a lot of really amazing data if you just threw away all of these censored patients. So really what we want to do is be able to train models that can use the entire data set and take into account this censoring bit. If this bit here is 0, then that is taken to mean that the time target is not necessarily time until death, but more so time until last follow-up, last be seen. All we know is that their time until death is sometime after this point. So that kind of motivates this kind of survival prediction problem, right? So here is like a flow chart, I guess, a general overview of what we want to do in this field. We have this data set of historical patients. We want to feed this data to a survival model learner. This will create a survival model for us. Once we have a new patient coming in, we don't have their time until some kind of event. At this point, we don't have like a censor value for them. And we want to give that to the predictor, and then we get some kind of prediction of survival so that various kind of medical interventions could be employed, or basically the doctor or whoever could just get a better general idea of the shape that this patient is in. Okay, so now I would like to go through a summary of approaches, I guess commonly used approaches in this field. And these are, like I mentioned before, nicely summarized in the Effective Ways to Build and Evaluate Individual Survival Distributions paper. So again, if you want more details on any of these, I would highly recommend taking a look there. So, survival model. What can this look like? What are the inputs and outputs? What are we trying to do with this survival model? Oh, wow, those slides flipping. I apologize about that. I feel like my computer's getting old. Okay, so this might seem kind of like weird and kind of a very highly information dense graphic, but I'm going to be going into basically each of these dimensions and give you a good way to classify these different types of survival prediction algorithms. So I guess I can talk about this as kind of like an XYZ plot here. So on, say, the x-axis, for any given survival prediction model, either it is going to return a probability of survival, and that could be at a given time point, it could be at many time points, etc., or it will output some kind of risk score, which ends up being a scalar value. And that can be used to maybe rank patients based on the risk that they have, say going into like a medical procedure or something like that. On the y-axis here, we have the number of values that the model will be outputting. So that could be many values. That could be one value for kind of all time for the patient. It could be one value at one time point. I'll go into each of these in a little more detail. And finally, on the z-axis, we have whether the model is good for making predictions about an individual, or if the model is good for making predictions about some kind of group or cohort. Okay, so axis 1, probability versus risk. So this describes whether a model will provide a risk score, which is again some kind of real number, or if it gives a particular survival probability where this probability value is going to be between inclusive, the values of 0 and 1, where 0 is like at some point a 0% chance of survivability. Basically the model saying there's no way this patient is going to be alive, like say at this particular point. Or if it starts out at 1, that's maybe like day 0 and the patient's currently alive. Like at day 0, we know that the patient's still here. So a drawback of risk scores is that they're really only useful in some kind of comparison. So, if say a risk for a patient is 8 and a risk for another patient is 1, say kind of like Mr. Dummy over here. If you just say like for patient Z, the risk is 8, that doesn't really mean anything in particular unless you have the context of the risk scores for other patients. Beyond that, though, probabilities can be used standalone. So, you could say, for example, with what probability will patient X survive a liver transplant? So say if you have a liver, you have 2 patients that you want to potentially give this liver to. If you have the risk score for this first guy being 1.31, meaning that maybe the risk of the patient dying would be, comparatively low to then this other patient who has a risk score of 8.67. You could use that risk score to then assign who would be getting, say, this liver for a liver transplant. However, a probability can provide a little bit more information. So, for example, say with a probability of 39%, this first patient is going to survive the liver transplant. And then with a probability of 7%, this patient is going to survive a liver transplant. Potentially neither of them get the liver in this case. You could make some decisions kind of outside of just which of the 2 of them should get it, because again, the probability can be used in a standalone context. Okay, so axis number 2, as I mentioned before, is the number of values that a model gives. So there's a little bit of a tricky notation here. So the first one would be kind of like one value at a particular time point t here. Next would be one value given for kind of like an overall survival. And then this infinity symbol here is when the survival model will produce some kind of function that can be evaluated basically at any given time point. So if there is a 1 in this notation, basically, yeah, the model outputs 1 or a small number of values. And I say 1 or a small number of because, as I'll talk about in a few slides, this distinction isn't always perfect. And then, yeah, infinity values in the form of a function is the kind of the other more different of the 3 classes. So up here, this would be an example of something that would be classified as this like infinity of the 3. And then finally, axis 3, we have group versus individual, denoted I versus G. I think this one's probably the most intuitive, but again, distinctions can get a little messy. This will describe whether a model makes predictions about survival for either a group as defined by some feature. So maybe it makes predictions about the survival of all people with like stage 2 liver cancer or something like that. I don't really know how the cancer stages work in particular, but that just kind of sounds like it could be plausible. Or whether it will predict survival for an individual trained on a large number of features. And by a large number, we can, again, that gets fuzzy, but for sure, a model would be denoted I if there's like a dozen or more features that were being used as input to train the model off of. Okay, so let's take a look again at this graphic here. So now that I think hopefully you have kind of a good idea of the different ways we can categorize these models, if one wanted to, they could start to put different well-known survival models on these planes here, right? Based on where they fall. And I personally think that being able to categorize these models in different ways is a really great thing when it comes to making decisions about which of these models should be employed in different contexts. Okay, like I said, problems with distinctions this can be somewhat blurry. So the one at a time point, one at all times versus infinity. Sometimes for the one at a certain time point, there will be models that choose arbitrary different time points, like predicting survival at 1 year and 5 years and 25 years. That's not exactly like a prediction of one value, right? And generally the one prediction for overall survival with this kind of upside down A here, that is more often associated with risk scores than it is with probabilities. Additionally, predicting or figuring out whether a model predicts for an individual versus a group, say if you have a model that uses like maybe 2 or 3 features to make these predictions. While that is technically on an individual level, generally that will be clustering patients into kind of smaller groups, which kind of then acts a little bit like those group predictions as well. Beyond, it's pretty easy to figure out whether something predicts a risk score or probability. It's just whether the values are between 0, 1, etc., and some other things as well. So that's a little bit more clear cut. But one might have already intuited that you can use models that give probabilities for ranking purposes. You could treat a probability as a risk score. If somebody has a 7% chance of having some kind of like adverse reaction to some kind of transplant versus somebody having a 40% chance of some adverse reaction, you can very easily use those to rank patients based on like survival. If you have models that predict or give you some kind of survival function where you can evaluate this function to get some kind of maybe probability or risk score at any given time point, you can easily see how you could use that output to get one value for a particular time point. And then beyond that as well, these group models can be used for individual purposes. So if you have a survival curve generated for a group, then you take an individual from that group and basically just assign them whatever value would have been predicted for that group because they have membership to that group. So you may be asking, what model type is best here? So recall, you can kind of use probabilistic models for risk purposes, et cetera, et cetera. You might ask, does this like probabilistic infinity value group model provide the most information? The answer is no, because these individual models are personalized to the individual, and that ends up being really, really important for personalized medicine. So because of that, it is easy to argue, I think anyway, that the models that give probabilities, the models that also provide some kind of survival function, and the models that are individualized contain the most information that could be helpful in a clinical setting. And this might be my own bias, having worked on a survival prediction task in this area, but I think the argument is sound here. So how do we measure the effectiveness of a model? This really, of course, depends on the type of model, and also highly depends on the medical task that the model will be used for downstream. I have this cute little picture of like a coffee robot here that I guess this robot's sole job is to bring people coffee. And in that case, you could come up with some kind of measure of like AI effectiveness or robot effectiveness. If the robot effectively brings you coffee, that would be effective. But it really is highly domain specific on how to define this model effectiveness generally, as many models are used for many different tasks. But I'll talk about a few main metrics that are often used in this field. So I will go over concordance, L1 loss, 1 calibration, Breyer score, and decalibration. So first I want to talk about concordance. This is an extremely ubiquitous measurement of model effectiveness in the survival prediction world. It's certainly not perfect. I've heard many people criticize concordance, but it is a very kind of easily interpretable metric, and therefore you do see it everywhere. So this is just a really simple example to illustrate what concordance actually measures. It is very sensitive to the effectiveness at ranking different individuals. So on the left here, we have 5 different, say in our case, patients. And for each patient, there is a time of death. So patient 1 died on day 1, patient 2 died on day 3, et cetera, et cetera. And here's this risk score, which is the risk that our particular model had predicted for this patient. So for patient 1, it predicted that this patient was extremely risky, extremely at risk of some kind of death event. And say patient 4 is a low ranking risk patient. So what concordance will do is it will take all potential pairs of these patients, and when comparing, say, patient 2 against patient 1, what it cares about is that if the risk score was predicted highly for, say, patient 2, and patient 2 actually died before patient 1, if patient 2's risk was higher than patient 1, then in this case, in this little table, it would get a little plus mark. And so once you have all of these comparisons made, you would just sum up all of the times that the model correctly ranked 2 different patients and divide that by the total number of comparisons that there are. In this case, it got 7 of these rankings correct out of 10. Therefore, the concordance would be 0.7. This is highly related to the area under the curve as well. And I'm sure if any of you are in kind of this domain or even machine learning in general, you see AUC everywhere. So concordance is relevant to choose as an evaluation metric when the goal of the model is to rank or discriminate between patients. So if you have a question like, which of these patients will live longer? Say you don't really care by how long, concordance would be a good metric for that. Maybe which of these individuals should get a heart transplant, for example, not at what point should each of these patients get a heart transplant, or which of these individuals should be admitted to the ER first if you have a long list of people waiting to get into the ER. There are also many extensions of concordance, such as time-dependent concordance. I won't go into a lot of those, but many people have been liking the idea of concordance and adding their own extensions to it to make it suit their particular model types a little bit better. Okay, next I'll talk about L1 loss. So as I had mentioned before, survival prediction is extremely similar often to regression. So why not, at this point, adapt some common measures of success that are often seen in regression? In particular, L1 loss is favored over something like L2 loss because it is less swayed by survival outliers. And survival outliers are very common in these data sets generally. So L2 loss, instead of taking the absolute difference, will take the square of the difference when evaluating this kind of equation at the top here. And so if you're squaring the difference, yeah, the outliers in the data set will just cause a lot more of a ruckus. So you would want to use L1 loss when the goal of the model is to predict survival time with the lowest absolute value difference. So if you're dealing with sensitive timing of targeted interventions, and you care less about the ranking between patients, but you care more about getting the timing as precise as possible, then L1 loss would be what you would maybe want to be considering when figuring out which model is performing best. Sorry about this. My computer is really bad at like, I don't know. I don't even think I have that much running. I closed all of my other tabs, but apparently that's not enough. Okay. The next evaluation metric is one calibration. So I would like to introduce to you the Weatherman test. The test here is on some particular day T, predict the probability of rain on day T+1. I think this picture was taken from some weather station where the weatherman was embarrassed because he got the forecast wrong, like really wrong or something like that. But imagine this weatherman, Mr. W, predicts that there is a 30% chance of rain 10 times in a month. If Mr. W is one calibrated, models are either one calibrated or not, and this is tested by doing a p-value test. We would expect it to rain 3 out of those 10 times that Mr. W predicted a 30% chance of rain. So one calibration generally is just used as a sanity check, and it shows that a model's predicted distribution matches that seen in reality. There's also Breyer score. This is a slightly newer metric that is common because it measures both discrimination, so the model would have a high concordance, hopefully, and calibration such that the model would be one calibrated. And this solves the issue where potentially this weatherman can be one calibrated, and that's a great thing. But then you start to notice that it rains less often when the chance of rain he predicted to be 80% than when the chance of rain was predicted to be 30%. And frankly, if this happens a lot, this person is probably not a very good weatherman. So you would also want to be taking into account discrimination along with calibration. So Breyer score just kind of marries the two of them together. Okay, and this last metric I want to talk about is decalibration. So this was introduced in that review paper that I had mentioned previously. This is a fairly new measure specific to individual survival distributions. So while I had argued that these individual survival distributions are contain the most information that we would want to know in a clinical setting to predict survival, they are generally, I think, some of the hardest to learn, and only more recently has there been strides made in this domain. So what we wanted to do is contribute a way to measure their effectiveness specifically catered to this model class. So that has that probability, predicts a survival function, and is individualized to a particular person that we want. This answers the question, should the patient believe the predictions implied by their survival curve? So I have here an example of 4 different patients. So we have patient A, B, C, and D. Each of these patients have a particular individualized survival curve. So on the y-axis here, we have survival probabilities. So at day 0, all of their survival probabilities are at exactly 1 here. And then as time goes on, this curve is generated at day 0, basically. As time goes on, each of these particular patients now have an individualized function describing how likely it is that as time goes on, there is going to be some kind of event. So I'd like you to take a look at each of these patients and quickly try to figure out which patient you would most want to be. You can pause the video, I guess, and take a look at this. Personally, I would like to be patient A, because once you get even up to day, whatever 70 this is, they still have like perhaps a 60% chance of survival, whereas things are not looking quite so good for patients B, C, and D, especially not patient C. But what is notable here is each of these blue lines represent when the patient actually passed away in this particular case. And we can see that for each of these patients, they ended up passing away in a particular time related to what the model predicted their median survival time to be. So once you have an individualized survival curve, the median predicted survival time becomes kind of an important way to distill all of that information from the survival curve. And what decalibration aims to do is measure that the correct number of patients are, say, passing away before their median survival time and after their median survival time, because of the nature of the measure of median. That definitely should be the case. You can also, instead of just splitting it into before and after median, you can start to split it into quartiles or even more quantiles after that. And basically, you can do some statistical testing to make sure that according to the model, the right number of people are reaching their event in those particular or between those particular boundaries that would make sense. So again, answers the question, should the patient believe the predictions implied by their survival curve? Yeah, I have a little bit more a figure that goes into just a tiny bit more detail. So the right side shows a calibration histogram. This is when the predictions are split into 10 different bins. Basically, in order for a model to be decalibrated, you would want each of these bins to look as though they are particularly or pretty equal in size, I would say. You can also see that as the percent chance of survival, the median survival, I guess, ends up being lower, you see that out of these, more and more of these patients are censored. So in this data set, it looks as though about maybe 50% of the patients are censored here. But yes, so as I said, decalibration is just another kind of sanity check, kind of like one calibration that will tell people whether they should be trusting the outputs of a particular model. So now that I've gone through all of that, I want to give some examples of the different classes of models. I'm only going to go through 5 here because if you think about the graphic I had shown with the different axes, that there would just kind of be like too many to go through, but these are like 5 kind of well-known, more of the interesting ones, I believe. So this first one here are models that fall into the class where there is one value predicted on an individual basis that gives a risk score. These are most often evaluated using concordance, again, because risk is good for ranking. An example, which is really, really common, that is used all over the place, is the Cox proportional hazards model. It is an extension to just regular linear regression. And lots of work has been built upon this Cox PH model. For example, we have DeepSurv, which I imagine stands for deep survival. And it is a Cox proportional hazards model that's basically just souped up by a deep neural network that allows for a bunch of kind of data kind of pre-processing augmentation with this huge number of layer weights. So X here is a vector of the patient features. It goes into a fully connected layer. There's some dropout, fully connected, just I guess dropout to prevent overfitting. Near the end, you get a kind of a linear combination of this set of now features that have gone through all of these different layers. And at this point, at the end here, it's predicting the log risk function, which is this right here, which is then used to predict some personalized treatment recommendations. So here is a good way to view just like regular, like a Cox model here. This lambda is the hazard function, the function that predicts the risk. So it'll be like the risk given this particular time, or the risk at this particular time given this set of features X. This is the baseline hazard given a particular time. So for anybody, what would the hazard kind of be looking like? And then it's augmented by this log risk function here, which is exponentiated. So that's deep serve. And I'll go to the next slide as well, if I can. Okay, so the next class of models I want to quickly talk about is the single time group risk predictors, also called prognostic scales. Again, because of that risk, they're typically evaluated using concordance. And an example here is the palliative prognostic index, which computes basically a risk score for terminally ill cancer patients. Based on those risk scores, you can group patients into different clusters. And then based on that group membership, you can predict survival at 3 weeks. So I even have a Kaplan-Meier curve, which I'll talk about in just a second, where you can kind of start to see that this group A, group B, and group C, if you look at their percent chance of survival over days, you can definitely start to see that groups A, B, and C really do separate out from each other. And obviously based on this risk score, this PPI, the palliative prognostic index, that does contain information to separate the patients into these meaningful clusters. Okay, then we would have this next class, single time individual probabilistic predictors. These are typically evaluated using one calibration or a Breyer score because they do provide a probability. You would want that calibration sanity check. Of course, also, if you're using Breyer score, it will be measuring the model's ability to discriminate as well. An example here is PredDip, or predicting depression. This uses survey responses to predict if a patient will develop some kind of major depressive episode or experience some kind of major depressive episode in the next 4 years. I'm not exactly sure how they decided on 4 years, but apparently that's something that has some kind of clinical relevance. This is an online tool, and I have a little picture of it up probably really soon. Wow, my computer's really going through it. Okay, so this is just a website you can go to, predictingdepression.com, and you can take the survey, fill out a few questions, and it will assign you this probability that you will undergo some kind of depressive episode in the next 4 years. Okay, next I want to talk about group survival distributions. So predicts probabilities at any number of infinite time points for a group. Once we get into the realm of these survival distributions, you can really evaluate these using any number of evaluation metrics. So you can use concordance, L1 loss, one calibration, Breyer score, decalibration, many more that I also haven't really talked about. Really, the only example that I think is worthwhile talking about from this class of models is the Kaplan-Meier model. Highly ubiquitous. This is everywhere. It was even in that previous example that I had just shown. It also has many uses beyond survival prediction. And I'll go into how these are generated. They're really actually quite simple. But what people will do is plot, say 2 or 3 or whatever separate Kaplan-Meier curves, and you can do some statistical testing to see if those resulting curves are significantly different from each other. So in this case here, say somebody has a gene A signature, and as part of some kind of if someone's like a patient with some disease and they have this gene A signature, this is what their survival outlook looks like. Whereas if they have this gene B signature, their survival looks slightly worse. And so, yeah, you can use Kaplan-Meier plots to try to tease out whether there are significant effects that, say, some like treatment group or being in possession of some kind of like, I don't know, gene mutation or something would have. So the Kaplan-Meier curve is created by taking a look at the survival times and the censoring bits of all of the people in your data set, people in your group. So the curve starts out at the survival probability of 1 up until the point where there is the first event. So at event 1, looks like at day 1, one of the people in this population died, and their overall looks to be like 10 patients. So it would bump down to then a 90% chance of survival, because at day 1, 90% of the patients are still alive. Day 2, there was another event where somebody passed away, bumped it down to at day 2, 80% of survival for the group. If there is censoring that happens, so if we lose some patients to follow up at day 3 and day 4, that doesn't bump the curve down any steps, but we do denote it by using these little tick marks here. And as time goes on, we would continue to move the curve along, and once we have reached the row of the data set that has the largest time to event, at the end, that's when we stop plotting. And then the resulting curve at the end is the Kaplan-Meier curve. Here's an example of a Kaplan-Meier curve from some publication. They have 2 different treatments, and so they gave group 1 treatment A, group 2 treatment B, and just plotted the Kaplan-Meier curves for each of these groups. And then they did a log rank test and determined that with a p-value of smaller than 0.0001, these curves are significantly different, meaning that the treatments have some kind of effect, or there is some kind of difference in effect between treatment A and treatment B. Okay, and then finally, we have this probability infinite values and individualized, aka the individual survival distribution. This is what I kind of care about. Once again, because this is a distribution, it can be evaluated using concordance, L1 loss, 1 calibration, bar score, decalibration. And an example of note is multitask logistic regression. This models survival using a series of dependent regressors. And if you're interested more about what that means, feel free to take a look at the NeurIPS paper from 2011 or send me an email. I've used this model a lot and I like talking about it. And this was out of the University of Alberta. This was out of the Greiner lab. Here's an example of what an MTLR model output would look like. So we have these 10 different patients, and MTLR was able to create or predict what the patient's individualized survival curve would look like. So again, patient 1 here looks like out of all of them, I would want to be this first patient. Their prognosis doesn't look too bad. But then I certainly wouldn't want to be patient 10 here at this point, who doesn't look to be doing too well. If you were to use a Kaplan-Meier curve, which would, instead of individual here, be group, all of these patients would be grouped into just one survival curve. And so you can start to see how that is not going to provide enough information to make sensitive medical decisions. So there's a tool online called PSSP, which uses MTLR and basically allows anybody with their own data set that has some kind of survival time and censoring bit to use MTLR in a really easily accessible way and get some really interesting visualizations and survival predictions for the individuals in the data set. And so I would like to very quickly do a demonstration of this tool as this last part of this lecture. I just think it's interesting. Hopefully you can see that. Okay, so once you visit this pssp.server.yaleborder.ca, you will be greeted with this page. You don't need an account, but because I've been using this tool for so long, I do have an account. If you go to the drop-down menu here for predictors, you can take a look at public predictors here. These contain a lot of different data sets that are interesting that this MTLR model has been run on. So there's even folders. You can see how this would work on different percent censored data sets. These are, a lot of these are cancer. And so here you can see how many instances versus how many features. You can see the concordance because again, that's a very commonly used metric. And then you can also see these chi-square values and the p-values, which have to do with decalibration. So I would like to just quickly show you some of the predictors I have. Maybe I'll take a look at this one. Breast cancer clinical only. This was from the TCGA dataset, the Cancer Genome Atlas. Looks like this doesn't have any genetic data in it, but I think should still be interesting. I just want to show off some of the things that this site can do. So you can take a look at the data set. It keeps it so you have the file. It'll tell you the number of samples and also the percentage that is censored. So in this case, this data set is almost 86% censored, which is quite high, especially when you're trying to predict survival time and you only have survival time for like 14%. So for all intents and purposes, I think this model does really, really well. You can take a look at the predictor settings, how long it takes to train. And then you can also look at the cross-validation results. So for example, this got a concordance score of 0.7. And you can take a look at all of these kind of different statistics as well. These include a couple more than what I talked about and a couple less of what I talked about as well. I think at this point, Breyer score wasn't as commonly used, but it is decalibrated. So in that case, we would say we would want to trust the model. We could look at individual predictions here. So this will just sample a number of the patients from the data set and show their different survival curves. So we have this patient who's looking pretty good, and then this patient who is kind of separating from the group in kind of a more negative way, kind of the opposite way. You can actually look at the specific predicted time to event for everybody. You can look at the decalibration histogram as well. So I had shown an example of that. So in this case, oh yeah, this data set is so highly censored, but you can see that within the quantiles, we would want, since the number of bins is 10, we would want about each bin to have 10% of the patients, and it looks like that is certainly the case. And then you can look at like the Kaplan-Meier visualization. Based on the PSSP estimates, it bins these patients into kind of these different groups and shows what each of them look like, and you can play around with that. Yeah, which I think is pretty cool. And then you can also take a look at the feature weights to try to figure out which of these features, and these are specifically clinical features, that ended up being important. Yeah, so there's a ton of other features as well. If you have any data sets that you want to test out, I would highly recommend playing around with this tool. And pretty much that brings us to the end of this lecture. Thank you all so much for watching. If you have any questions, please feel free to reach out to me at sdavis1@ualberta.ca. I really like survival prediction, and I'm always happy to chat with people about it. All right, here are the references. Yeah, take a look if you like. And yeah, I hope everybody has an excellent morning, afternoon, evening, weekend, week, month, whenever you're watching this. This is part of the application stream of the AIMS AI Medicine curriculum, and there will be a quiz available to you at the end of this as well. All right, thank you so much, and I'll sign off. Bye-bye.